So this is a bit of a sneaky question. You're asked to calculate the change in entropy with a change in pressure while the temperature is constant. So we would immediately think of going to our expression for a change in entropy as a function of change in temperature and change in pressure as it is written on our data sheet. However, if we look at the shape of this Redlich-Kwong equation of state, it is obvious that in order to get an analytical expression for this slope, you need to be able to isolate the volume from this equation, and that is going to be a tricky exercise if you want to do it analytically. What we should realize now is that at state 1, we know the temperature, we know pressure 1, and subsequently, from this equation, with a little bit of work granted, we would be able to calculate volume 1. Same thing at the end state, temperature, pressure 2, we would be able to calculate volume 2. In other words, we might as well express the change in entropy as a function of temperature and volume and see if we can derive a more convenient equation to use. So here we go. The total change in entropy is the partial change with temperature while I keep the volume constant, and the partial change with a change in volume while I keep the temperature constant. For our problem that we're currently busy with, it's an isothermal process, so we do not need to worry about that. Make sure that you can actually prove that this is equal to Cv over temperature dt in that equation. So if we go to our Maxwell equations, have a look at your data sheet. For this slope there, we can immediately show that this can be related to the slope of how pressure change with temperature while the volume is constant. After substitution, we can prove that the change that we now have to calculate looks like this. And if we look at our equation of state, this is something that we can now easily do because there we've got temperature to the power of minus half, and we can get the value of that slope, which we can then integrate between volume 1 and volume 2 to get that final expression that's given on the memo. Just a hint, when you have to integrate this expression, you may need to remember something about integration of partial fractions. You can write this in terms of some a over x plus b over 1 plus x. No? So, good luck with that. I'm not going to show the full derivation of that expression. For determining an expression for delta U, do not be tempted to derive an equation in terms of temperature and pressure. You're going to run into the same set of trouble. So rather have U as a function of temperature and volume, and then you can use the equation of du that we derived in the lecture slides, and that is given on the data sheet.